Hi children and hi everyone. In previous video we discussed about the working of telescope. In this video I am going to explain very interesting topic in interesting chapter. So today we are going to start the new chapter, wave optics. In that I am going to explain refraction phenomena by using Huygen's theory. So this is the topic for today. So very interesting topic and very interesting chapter too. So examination point of view also very interesting chapter. So children, here already we know that we have so many properties of light: rectilinear propagation, reflection, refraction. So in this case the wave theory was first the light should be transmitted in form of waves. That should be proposed by Huygen. He was given one wavefront theory. So here, according to Huygen, the light should be transmitted in form of wavefront. Clear children? So here now, first we have to know about what is wavefront. So what is this wavefront theory? Okay, so after that we are going to the topic. So here we know that when we have some calm pool, steady water is there. In that steady water, if we can drop a stone, what do you observe? Some disturbance is created. For example, imagine now this is a calm pool. In that pool, you drop one stone. Then the disturbance created, and that should be equally transmitted in all directions. The disturbance what it is created in all directions should be same. While we are dropping the stone, if you can capture a photography, you can find like this only. The disturbance is created and that should moves in all directions is same. Here in this direction and in this direction, the disturbance will be transmitted in all directions. In the same manner, if you can take a source of light, for example here now I am taking, this is the candle here, I am taking that candle is the source. So here it is the source that emits the light. Then also here the light should be spread that can move in form of the spherical wavefront. Clear? So here when we are having a tube light in a room, in that room we are getting same intensity of light throughout the room. We are not finding any variation in intensity of light in the same room. In a closed room we have one tube light is there or any light source is there, that should be emits the light in all directions. So here we never find any difference in intensity of light in the same room. So he was given one explanation for that to justify this answer. That answer is here now. What is meant by here wavefront means, here now this is the one source. The light coming from the source, that should be the different particles, the light should be having same phase. Clear? What I told you, when the source of light is there, the light should be transmitted in all directions with the same speed and same properties. Huygen's explained that he was imagined one concept of medium. That medium is ether. Medium is what? Ether. According to his assumptions, that ether medium is having nature of elastic and inertia, and that medium is, he was taken homogeneous medium. Homogeneous medium means what? That should be having same density everywhere and having the same properties like inertia and elasticity. So I hope you know about the inertia and elasticity. So that's why here, according to Huygens, he was assumed there is one medium, ether, that is the homogeneous medium. In that we are having, that is having some two properties, inertia and elastic nature. So in that homogeneous medium, the light should be occupies and the light should be spreads in all directions with same speed and same properties. When they have same properties, the locus of all the particles which are in the same phase of vibration, that should be taken as a wavefront. That means here, now this is a source and I am taking here, this is a, at these points, the particles which are reaches, that should be having same phase of vibration. So here now, this is the one light ray and this is another light ray, this is the another light ray, like this. So here I am simply having, just imagine, actually that is wavefront concept, but I am just, to understand that I am telling you, now it is a light ray, simply imagine. Then the particles which are having same phase of vibration, those should be taken as here wavefront theory. What is that? Wavefront. So he was given one explanation for the why the intensity of light is same everywhere in the homogeneous medium. Why there is no loss of intensity of light in particular homogeneous medium means he was given one particular explanation, that is here, this is the source. This is what? Source. After that source, from distance, at some distance from the source, we have different particles are there. These particles are here having same phase of oscillation, then the locus of all the one, here this is 1, 2, 3, like this. So the wavefronts here coming there, simply the locus of this one. To understand that, he was given one concept also, he was showing like this. This is another wavefront and this is another one and this is, and now so he was given one explanation that he was taken, if you just imagine the light is moving in this direction, he was given that the light must be moving from the source in form of these spherical wavefronts. So here in this diagram you observe that the wavefront should be like, it is now solid and there should be here some dotted lines. Here the solid here, there should be giving some positive and this is negative. That means here positive approach and negative approach he was taking consideration. So here positive means constructive. What is that? Constructive. And this is a destructive. So here while we are observed at this location, the positive should be touches here. Due to that, the intensity of light is same. There is no loss of intensity. And he was taking some points here. This is S1, S2, S3, S4, S5 and S6. Clear? When you have S1, S2, S3, S4, these are what? Points. What we selected? Some points. When we have selected some points, at those points the oscillation of light should be same. The points which are having same phase of oscillation of the light. Clear, children? The locus of all the points, simply you forget about this thing, simply here the light is coming in this direction in form of wavefronts. At particular this position, we have selected some points. These points are having some same phase of oscillation. Clear? Now here S1, S2, S3, S4, S5, S6. At these points they have same oscillation. I am taking this now AB. Now it is what? AB. Now the locus of all the points which are having same phase of oscillation, that should be called here wavefront. That's why here AB is what we call wavefront. AB is what we call wavefront. That's why here, according to the Huygens, the locus of all the points which are having same phase of oscillation, that should be called wavefront. According to Huygens principle, the points what we selected S1, S2, S3 up to S6, these points also can act as the secondary sources. Here S is the primary source. From the primary source we are getting wavefronts. So the locus of all the points what we get again? Another wavefront. On that wavefront we have some points are there. Those points are called here secondary sources. What is that? Secondary sources. So here again S1 can produce the wavefront and S2 also produces the light again. So S1, S2, S3, S4, S5, S6, these also acts as the secondary sources. Secondary sources. Secondary sources means what? Again they also produces the light. They also produces the light. Then here the envelope of here the light which is coming from these sources should be called as wavelets. What we call wavelets. Clear? This is the wavefront. The light is emitted by the secondary sources in form of wavelets. The envelope of all the wavelengths can give the another wavefront. Now I am saying now here A dash, B dash, A dash, B dash. That means what here? The light what it is coming from S1, S2, S3, S5, S4, S5, S6. It is nothing but what? S. Clear? The light what we are getting here S, that should be here in form of S1, S2 like that. Again we are adding the wavelets which are coming from the S1, S2, S3 and so on S6. The envelope of all these wavelets also construct the another wavefront. So according to his theory, the first wavefront AB and second wavefront A dash, B dash, these two also taken as here, they are having same intensity according to principle of superposition of waves. What do you write? S is equals to S1 plus S2 plus S3 plus I am writing here S6. Here when we have some again principle of superposition, from S only we are getting S1, S2, S3 like that. Again what we can add? Again we are adding these. Then what do we get? S. That's why in this way there is no variation of intensities of light at different positions. So the wavefront first one, wavefront B, and again same. Next thing, third wavefront, next one like that. That's why here the light should be transmitted in form of wavefronts from one place to the another place. There is no change in its intensity and other properties. So this is the theory given by the Huygens. Simple. How to remind this sentence only you have to remind. The first thing is what here? According to Huygens, the light must be moves in all directions in form of the spherical wavefronts. And in a wavefront, the points which are on the wavefront should be acts as a secondary sources. And the wavelets which are coming from the secondary sources, again they will be construct the another wavefront. like this. This is simply about the Huygen's wave theory. By using this Huygen wave theory, now I am going to explain refraction of light. Refraction of the light. That means we can prove the Snell's law by using this concept only. Clear, children? Very simple. According to Huygens, the light must be transverse in form of the wavefronts. The point which is on the, for example here, this is the wavefront. AB is the first wavefront. On that wavefront, we have some points are there, S1, S2, S3, like that. They should be acted as the secondary sources. Again, they can produce the light. That should be what we call in form of wavelets. Again, the envelope of next one is what we call secondary wavefront. In this way, the light should be transmitted from one place to the another place. So this is the concept was given by Huygens. Okay, now let us see refraction phenomena by using Huygens theory. To understand that, here diagram is so important. Watch carefully. So this is the one interface, P dash, that is what? One interface. That should be separates the both medium. This is the medium 1 and this is the medium 2. Clear, children? Medium 1 and medium 2. In this medium, the velocity of light is V1. In this medium, the velocity of light is V2. Clear? After that, here just see here, okay, look here in this diagram, you have to observe very carefully. Here this is medium 2 now. Look here, in this diagram, this is the one incident ray and this is the another one. I have selected here, this is the point A and this is the point B. Now AB is the wavefront. What is that? AB is the wavefront. Light ray is coming like this and this also like this. Here if you can select 2 points, those 2 points have same phase of oscillation. That's why AB is now here. What you have to say? AB is what? Wavefront. So here both are having same phase of oscillation. Clear? After that, at this point, if you want to again see this here, this is the interface and now this is one incident ray and here we are taken, this is another incident ray, this is the one point and this is the another point, A and B. Clear, children? Watch carefully. We are taken, this is the first ray, here incident ray. That's why I am drawing here one normal. That's why it is what we call angle of incidence. Just let us assume that what is that? This point A and this point B both are having same phase. That's why I am taking AB is wavefront. AB is what? Wavefront. So after that also here this is continuous motion towards interface. Clear? After that this incident ray is refracted like this. This is now refracted towards normal. Here angle of R is less than angle of I. So it is towards the normal. After that here to understand the shape of the wavefront, we have to construct one spherical wavefront. One spherical wavefront with radius V2 into T. What is that? With radius V2 into T. What we know, velocity is equals to displacement by time. Then x is equals to what, right? V into t. V into t. V is equals to x by t. X is equals to v into t. Clear, children? X is equals to v into t means what? Distance travel here. That's why here now distance travel is how much? V2 2. V2 into t. And that's why here with that radius we have to construct one sphere. Just imagine, this is only one part of the wavefront, spherical. From that, here I am drawing now here, this is the tangent now here. What is that? This is the tangent. We are drawing, this is the tangent. Clear, children? So here now this is equals to angle of R and this is equals to angle of I. Angle of incidence and angle of refraction. That is the diagram. Clear, children? Very simple. Let us consider we are having two light rays. For example, I am saying this is A dash and this is B dash. Clear? Clear, watch. Here now this is the incident ray and this is the another ray. Here there should be incident at this point A and this point is B. Here these two are in same phase. That's why I am drawing one normal. Then that should be gives the wavefront. Clear? Here you have to know that while the radius of the wavefront should be increased, that should be seems to be like plane wavefront. That means here, for example, now this is the source. If you can increase the radius like this, so after some time what you can see that this should be always seems to be like plane wavefront like that. So here this is also just part of the wavefront. Clear? That should be, seems to be like a plane. So after that, here it is moving from here to here and this is also moving here to here. Then here what you have to say, we draw some normal. Here this is the angle of refraction and angle of refraction is less than the angle of incidence. That's why it is having some refracted rays moving towards normal. And after that, this is the, according to these rules we have to take, this is the angle of refraction. So this is the concept involved there. Here you have to observe. In this case, we have to take one assumption, that is here the time taken by the second wave. The time taken by the second wave, because here A and B, at A and B both are in the same phase of oscillation. That's why the time taken by the B particle at B to reach this point, to reach the interface must be equals to the time taken by the wave, again here A to this one. So for example, I am using A dash A B and I am taking this now D and this is now, here it is E. Here what is the assumption? The time taken by the wave to move from B to D is must be equals to the A to E. A to E. Clear? So this is the refracted ray. And this is the angle of refraction. So here the distance moved from taken, the time taken to reach from B to D is equals to A to E. Clear, children? So here now we are going for derivation now here. In this case I have told you this is medium 1 and this is medium 2. Medium 1 and this is medium 2. The velocity of light is what? V1 in this case, and in this case V2. Clear? So here from figure we are taking the triangle now ABD. Triangle ABD we are taking. Triangle ABD. From the triangle ABD, what we write? Sine means what? Opposite side by hypotenuse. So here angle is 90 is there. That's why this is the hypotenuse. And here what you have? This is the angle of I. So this is what? Opposite side, and this is the hypotenuse. That's why I am writing here sin I is equals to BD by what you write? BD by what you write? AD. BD by AD, equation number 1. Clear? So here what you take? Here the time taken by the ray to move from B to D is what? T. Clear? I already told you what's that. Velocity is equals to displacement by time. Then displacement is equals to v into t. And the distance traveled by the second wave is what? BD. BD is equals to what, right? Velocity into time. Velocity into time. What is the velocity here? v1. And what is the time? T. That's why I wrote here v1 into t. Got my point, children? So in this case, we have taken what's that one assumption. Here, the time taken by the light from the point B wavefront. This is now what? Secondary source. A and B are we are taken 2 points. AB is the wavefront. On that point, on a wavefront, we have 1 point. That point acts as secondary source. That's why again the light is coming from secondary source. That should be reaches the point D within the time of t with velocity v1. Clear? Moving from B to D is time is t, with velocity is v1. Already we know that velocity is equals to displacement by time and x is equals to what, right? V into t. From that what, right? BD is equals to v1 into t. Like that I am writing now here what, right? In first medium BD is equals to what, right? v1 into t. Substitute there. Then sin I is equals to what, right? v1 into t by AD. Now equation number 2. Again over here I am going for another triangle from figure. Triangle AED. Triangle AED. Clear? From the triangle AED what, right? I am going to have sin R. Sin R is equals to what, right? AE by AD. AE by AD. AE by AD. So this is the distance traveled here and this is AD. 90 again here also it is 90. Then it is hypotenuse. Then this is the angle and this is the opposite side of 90 here. AE by AD. So in second medium what we write? AE. AE means what? Distance travel. Distance travel. X is equals again v into t I am writing. X is equals to v into t. What is the velocity in second medium? v2. And what is the time? T. The time taken by the right ray from B to D must be equals to the A to E. Because those are again secondary sources. That's why I am writing here. What do you write? AE is equals to v2 into t. Then substitute there here. AE is equals to what? v2 into t. Then substitute there. Sin R is equals to v2 into t by AD. Now this is equation number 3. Clear, children? So here now by using 2 and 3 I am writing now here again from 2 and 3. 2 divided by 3 I am doing sin I by sin R. From 2 and 3 we are dividing 2 and 3. Sin I by sin R. Sin I is what? v1t by AD by v2t by AD. AD cancel. Then what you get? Sin I by sin R is equals to v1t by v2t. AD cancel. What you get? Sin I is equals to sin I by sin R is equals to v1t by v2 by v1t by v2t. TT again cancel. Then what you get? Sin I by sin R is equals to simply v1 by v2. Sin I by sin R is equals to v1 by v2. So here sin I by sin R what we call? Almost all Snell's law. And now here we know that what you have n is equals to c by v. N is equals to what? C by v. N means what? I explained in previous videos in the optic chapter. What is absolute refractive index? Absolute refractive index is the ratio of velocity of light in free space to the velocity of light in the medium. So this here n is what? Absolute refractive index. N is equals to c by v. From that what we take? n1 is equals to c by v1 and n2 is equals to c by v2. Here c is constant, 3 into 10 power of 8 meter per second. That's why here what do you write? I am writing now here n1 by n2. n1 by n2 is equals to c by v1 by c by v2. Then what do you get? N1 by N2 is equals to what do you get? C by V1 into V2 by C. That means what? V2 by V1. What do you get? V2 by V1. Then I am writing here. This is the medium one, and this is the velocity V1. So I am writing there. N1 by N2 is equals to what? V2 by V1. Then V1 by V2 means what do you write? V1 by V2 is equals to what do you write? N2 by N1. Now substitute this value V1 by V2, what it is? N2 by N1. I am substituting that. Sin I by sin R is equals to what? N2 by N1. Then what do you write? N1 sin I is equals to N2 sin R. This is what we call Snell's law. What do we call? Snell's law. Clear? And from the diagram we have to observe one important point, that is what it is here. Simply this is the point of incidence and this is what? Point of refraction. So, and this is what? Normal ray. Normal ray, incident ray and refracted ray. Normal ray, incident ray and refracted ray all are in the plane of P dash. In the plane of P dash. So this is what we call second law of refraction. In second law of refraction, what do you write? Incident ray, refracted ray and normal must be at same plane or must be in same plane. So that should be possible only when the light is incident point. We have to consider, then incident ray, normal and refracted ray all are in the plane of P dash. So that's why in this derivation we derived what? Snell's law means what? That is the refraction. Sin I by sin R is equals to some constant. So that is the refractedology already here. And what we proved? Second law of refraction. Incident ray, normal and refracted ray all are in the same plane. So this is about the refraction of light by using Huygen's waves theory, wavefront theory or wave theory. Got it, children? This is 8 marks question for intermediate children. So see once again clearly I am explaining that. What is Huygen's principle? According to the Huygens, the light must be transmitted in form of wavefronts. In form of wavefronts. And again, at every point on the wavefront can be acts as the secondary source. This phenomena what we call Huygen's principle. The light must be transmitted in form of wavefronts and every point on the wavefront should be acts as a secondary source. Again these secondary sources can produce the wavelets. The envelope of all the wavelets gives another wavefront. Clear? So now we are going to explain some theoretical explanation for refraction of light. Watch carefully. In this case, P dash is the interface. P dash is the interface. So here two light rays are coming from different distances. Already I have told you what's that? The source can emit the lights in all directions. So primary source is there. From the primary sources are two waves are coming. Two waves are coming. To these two waves are at these points we are having some A and B. If you can observe at these points, those should be having same properties. Clear? That means A and B should be taken as here wavefront. Clear? So now AB is the wavefront and that wavefront should be incident. Now the AB is the wavefront that should be incident at this point. After that also the light is coming in form of wavelets. Further they are also emits the light. And for that, to understand, this is now one wavefront. I already told you the light must be in form of spherical wavefronts. When the spherical radius is more, in that some part should be seems to be like plane wavefront. Plane wavefront. That should be like this. It is not in the form of spherical wavefront. Clear? So it is the part of the sphere. Part of the sphere. So after that, to understand the shape of the another wavefront, we have to construct one sphere with radius. So now this is I am drawing here, this is one radius. How much it is? V2 into t. This is the radius. With this radius, we have to construct one sphere like this. We have to construct one sphere. So, we have to construct one sphere. For that sphere, we are drawing one tangent. This is now tangent. This is what? Tangent. In the second medium, we have to construct one sphere with radius V2 into t. What is the necessity to construct this sphere means we want to understand the shape of the wavefront. For that only we are drawing this spherical sphere there with radius V2 into t. Clear children? On that sphere, we are drawing here one tangent. Clear? So after that, this is the refracted ray. And now this is the angle of normal perpendicular these two. This is 90 and this is the angle of incidence and this is the angle of refraction. So that should be equal to here this one. Clear? After that, so we have to observe the two triangles. The first triangle is what? ABD. This is the triangle ABD. Children, this is also here 90. And this also 90. Clear? So already the side which is opposite to the 90, that should be taken as the hypotenuse. That's why here sine means what? Opposite side by hypotenuse. That's why here I am writing opposite side is here. It is what it is, angle is there. For that we have what is side, it is opposite side BD by, and this is 90. For that opposite what you have? AD. That's why it is AD is the hypotenuse. That's why sin I is equals to BD by AD. That is equation number 1. After that you have to go for one assumption. What's that? The distance traveled by the light from B to D equals to and A to T must be in the time of T. Clear? Because those are the part of the wavefront. They should be having same time taken. That's why here the time taken by the light ray to move from B to D and A to E both are same. That's why here the light is having velocity V1 with time T. Here B to D, the velocity, first medium is what? Velocity is V1. I told you already. V1 is the velocity in the first medium and time is what? T. Then distance traveled, what do you write? V1 into T. Distance is equals to velocity into time. According to that we are writing BD is equals to A1T and we are substituted there. Then equation number 2. And second triangle AED. From that what write? Sin R is equals to AE by AD. Again same concept. What is AE? Distance traveled in the second medium. Distance is equals to what? Velocity into time. In the second medium velocity is what? V2 and time is what? T. Then sin R is equals to V2 into T by AD. Equation number 3. After that we are dividing these two. What do you get? Sin I by sin R is equals to V1T by AD by V2T by AD. AD cancel. Then what do you get? Sin I by sin R is equals to V1T by V2T. Then again TD is same because time taken is same from B to D equals to time taken from A to E. That's why these T also cancel. Then what do you get? Sin I by sin R is equals to V1 by V2. So this is the ratio of I and R in terms of velocities. So we want to need in terms of refractive index. That's why I am going for now here absolute refractive index. What is that? N is equals to C by V. N is equals to C by V. The ratio of speed of light in free space to the velocity of the light in the medium. That is what we call absolute refractive index. N is equals to C by V. By using that I am writing here N1 is the refractive index of first medium. That's why C by V1, and N2 is the refractive index of second medium. That's why I am writing C by V2. Then N1 by N2 is equals to C by V1 by C by V2. Then what do you get? N1 by N2 is equals to V2 by V1. So we substitute this value in this equation. V1 by V2 means what? Here N1 by N2 is equals to V2 by V1. Then V1 by V2 means what? N2 by N1. Then V1 by V2 is equals to N2 by N1. Then what do you get? Sin I by sin R is equals to N2 by N1. So this is what we call Snell's law. In this way we can derive this Snell's law. So we are saying Snell's law means what? The refraction is going on. And next thing is what? according to second law of reflection, what do you say? First law is what? Angle of phi is equals to angle of r. In this case, I am going to explain here at the interface, normal, incident ray and refracted ray all are in the same plane of P and P dash. I already told you starting, P and P dash is the what? Interface of the both medium 1 and medium 2. That's why here what I have to say, in the plane of P and P dash, incident ray, normal and refracted ray all are in same plane. So that's why what you proved. In this way, by using the Huygen's Wavefront theory, we can explain the refraction of light. So children, I hope you understand. So if you can understand this video, like the video, share the video and comment the video, and for latest updates subscribe my channel and press the bell icon to get the latest notifications. Bye children, take care. We will meet in the next video with another topic. Bye, take care.